Hello, and thank you so much for tuning into this talk. My topic is how we could use neuromodulation to understand the human connectome. My name is Andreas Horn, and I work at the Brigham and Women's Hospital in Boston in the Center for Brain Circuit Therapeutics led by Mike Fox. These are my disclosures. When we talk about neuromodulation, there are non-invasive and invasive forms of neuromodulation. Non-invasive forms include TMS, TDCS, TACs, and so on. And invasive forms might include deep brain stimulation, focused ultrasound surgery, or other forms of ablative neurosurgery. I will focus quite a bit on deep brain stimulation in this talk, but many of the concepts I'm going to show might also apply to non-invasive forms or other forms of neuromodulation. So if you're interested in that, maybe there's something in this for you as well. Deep brain stimulation is a surgical approach where electrodes are implanted into deep structures of the brain, such as the subthalamic nucleus. And these electrodes often have up to 16 contacts now. So after surgery, these are implanted, they go with wires to the impulse generator of the in the chest of the patient. We can often then, as neurologists, tune which contacts to activate and also which combination of contacts to activate. With modern electrodes, we can even steer the field along the X and Y axis. This is the surgeon entering the electrode into the brain. And we see often this involves very meticulous planning using stereotactic planning software, and also involves a frame that's screwed onto the head of the patient. For people that have not seen DBS in action before, this might be the best way to demonstrate its great potential. This is a patient with Parkinson's syndrome that I took care of at the Charité in Berlin, and the only difference between the two videos is really that the device is on versus off. Right on the right, we see a much faster movement velocity, less bradykinesia and rigidity in the patient, and on the left, without DBS, we really see a very different movement pattern. Very critical to success is that millimeters matter. We really have to put the electrode to this specific spot. And for Parkinson's, it's really this spot in the STN, defined by Kerr et al., but also by many others by now. And this one comes very close. This is the active contact marked in red, had an 80% improvement. Now, this one is just 2 millimeters apart and only had a 30% improvement. Or 25%. So millimeters really matter a lot. And from a neuroimaging perspective, millimeters also matter when we reconstruct the electrodes, right? So this is, I sometimes even tell my colleagues, I think this is the royal discipline of neuroimaging, because we really obsess so much about the small details of where exactly we are in the brain. And to facilitate this process, we've come up with an open source software called Lead-DBS that's freely available and uses pre- and post-operative imaging data to reconstruct the electrodes. And some examples of usage include clinical uses under IRB approval. So this is one case where the team of Lan Lu at the BIDMC in Boston used Lead-DBS to localize an electrode, saw it's misplaced, and then reconstructed it better and planned where to put the electrode to match it better. So this is a group of electrodes. I sometimes envision that we could use technology such as Lead-DBS to better harmonize where the electrodes reside across patients. This is my essentially ultimate mission, to try to maximize the robustness and the comparability across patients, that every electrode is really implanted in the same optimal structure. And the current culmination of success of the toolbox has been a clinical trial led by Andreas and Jan Rödiger in Berlin, where they used Lead-DBS to suggest the optimal stimulation parameters for patients that led to an improvement that's comparable, non-inferior to the expert decisions. Scientifically, we're super excited. In a growing team, about 65,000 downloads, and also a growing team of people. Software is being used in all continents. What's even better than usage is that the development team grows. These are not all members from my team, and these are just the core contributors, but they are distributed across the globe, some in Australia, some in Europe, some in the US, and help make this a better tool. So if you're a developer and interested in open source software, please do reach out. We really need a lot more people to make this a great software. And of course, I want to mention that we're standing on the shoulder of giants. So I want to pay tribute to these amazing open source toolboxes that Lead-DBS builds upon. So everybody has seen the power of what an open tool can do, such as SPM or FSL and so on, for the field of fMRI. And with Lead-DBS, we try to do essentially the same for the field of deep brain simulation. I thought this is OHBM. People here are usually not dealing with electrodes in the brain. What could be in it for them, right? What are the features that Lead-DBS brought that are useful for DBS that could also be useful for general neuroimaging? And I came up with a few things. So first of all, the software comes fully packed with subcortical atlases. Again, many of them not from us, but from great colleagues that shared their data to be included in Lead-DBS. So all of these are nifty files, can be downloaded, can be used outside of Lead-DBS very easily. The same with whole brain atlases. So we have a large collection of volumetric whole brain atlases we use for connectomic mapping as well. Lead-DBS uses BIDS, the new horse of the standards of how to store neuroimaging data. So if you, cross talk between, let's say, fMRI prep and Lead-DBS, that's now very easy. You can set up scripts in the same folders and, pair outputs and inputs across the software pipeline. So this is a major endeavor, was a major endeavor also for Lead-DBS, but is a great endeavor for the neuroimaging community, I think. Lead-DBS is a nice all-purpose visualization tool. So whether it's really just for a cool figure in your paper or something that's actually related to DBS, you can use its viewer to look at nifty files, for example. Just drag them onto there and you see them in 3D. There's also, a nice way to visualize heat maps. So you can drag in surface and then overlay a nifty file as a heat map and look at it that way. So it's really a nice general purpose viewer. This is another example of scripting-based, tracks that associate with fMRI task activations in a fixation versus checkerboard task, just to show a bit also the visualization purposes of Lead-DBS. Now, maybe the most interesting part of it is really that it might be the ultimate or one ultimate normalization toolbox, because you can use ANS and all the FSL tools and also all the SPM tools all in one convenient UI, always with the same inputs and outputs. And, it takes care for you about differences in the warp fields, how these, software tools are storing them. Also co-registrations, using BrainsFit, ANS, FLIRT, and so on, hybrid forms of SPM and ANS and so on. So it's a really nice all-purpose registration toolbox. But since we obsess so much about millimeters, look at the cerebellum here, right? This is a normalized brain. If we compare that to the MNI brain, there is a mismatch here, right? With WarpDrive, we can fix that. We can essentially take the mouse and drag the cerebellum up and make it fit better, right? So this is in my view a really nice tool if you press normalization somewhere and it just doesn't look perfect, but you want it to be perfect. Use WarpDrive to manually fix it. We can really go into details here, right? In our field, we often care a lot about the subthalamic nucleus, which we see here, this structure. This is the red nucleus, and this is the STN now of the MNI brain. And we have an atlas that perfectly matches that. So this is the distal atlas. Now, if we fade back to the normalized STN, we see there's a mismatch here. Again, we can fix that with WarpDrive by manually dragging it over. And that works on the warp field level. So this could really be a cool tool for very different applications like histological to MRI registrations and so on. There are different tools. You just saw the drawing tool. This is another like lightweight video just showing how to manually drag things around there. And this is again the red nucleus. We have some mismatches there, so we can draw and fix it. We can also reverse that to segment the brain, right? We can go from MNI here. This is native space now. This is a misplaced, registered STN. We can fix it to be correct and then use that to segment brains. So in a way, this is a new form of segmentation where you take an atlas that's maybe more or less correct, put it into patient space or like native space of a subject, and then drag it around to make sure it fits everywhere, and then burn it into a nifty file to have a segmentation. And then finally, we could potentially use it for the cortex. I've never done that. Like we don't care so much about the cortex, but this is the Edlow brain 100 micron ultra high resolution 7 Tesla scan, which has been registered to the MNI brain. I tried to do my best there, but somehow not always perfect. Now, if we really care about this specific gyrus, we could use WarpDrive to fix it. And potentially, I'm no expert there, but it could be interesting for layer fMRI as well, right? To really make sure all of the cortices are, perfectly registered. And I know most people would use surface-based reconstructions here, but if you want to maybe also combine it with tractography, then maybe surface data is not perfect. Or if you really care about the subcortex, then again, surface registrations might be suboptimal. Now, maybe a minor point, it also comes with a fully fledged fMRI and DMRI processing tool. You can run, matrices and centrality estimates and so on. I think there are better tools out there for this, but Lead-DBS can be, fun, especially if you also deal with deep brain simulation and connectomics. So in essence, don't be fooled so much by the DBS in the name. Lead-DBS could be for you as well. Give it a spin. Maybe there's something in it for you. But you might wonder now, okay, what do we do with it? If we're not eating pizza, as in this picture, what we really care about is brain circuits. So in order to modulate the behavior of the brain with DBS or with other things, we want to know the circuit that we have to modulate first, right? So the circuit defines where we put the electrode. And the same, I think, applies to TMS as well, non-invasive forms of neuromodulation. So defining that circuit is key. We want to know which circuit, for example, codes for tremor in Parkinson's disease, right? How do we do that? Of course, there are animal models, right? But translational value is always a bit unclear. There's fMRI and PET, which a lot of you use, us use as well, right? But we could scan Parkinsonian patients and healthy controls, contrast them, see the difference. That's a circuit. But some of these differences might be compensatory. They might not even be causally linked to tremor. And then even if we use electrophysiology, it's not clear if it's a causal mapping of what we see between, what in the brain versus in real life. So at our center, we came up with a different way to do this, to reverse the problem and use the DBS sites and the TMS sites to define the brain circuits in the first place. And we also do so with brain lesions. So stroke lesions that lead to a specific symptom. If they all map to the same circuit, then we know, or we can conclude, that this circuit might be important for a specific symptom. How do we do that? So these are electrodes, again, reconstructed with a Lead-DBS. We have the stimulation volume in red, and we look at which tracts go through it. We can do the same for fMRI as well. So these are the two workhorses, as many of you will know, of course, resting state fMRI, a non-invasive form to estimate functional connectivity in the brain, and then diffusion MRI, a non-invasive way to estimate structural connectivity or anatomical connectivity in the brain. And I say estimate because both are essentially not great, right? In fact, for diffusion MRI, which I focus on a bit, we have really gone away from running, whole brain tractography and just using that without checking it. We even sometimes use histology to define the tracts or other sources of information. And if we do diffusion MRI, we often have to manually curate the tracts. So this is one example. The reason is that there are so many false positives in normative connectomes, but also the small bundles we're often interested in for DBS, the ones that connect the STN and the GPI and so on, they're really not, easily to reconstruct from diffusion MRI. So we have to create these manually curated tract atlases. And one great example is this one from Cameron McIntyre's lab and Mikkel Petersen, which is a tract library that's not even built using diffusion MRI. This looks like a tractography picture, but in fact, it was 4 anatomists that use holographic lenses to draw the tracts in stereotactic space and really register it with histology and so on. So we really obsess about the small tracts, about the details of where these tracts go into the STN and so on and so forth. To now look at which of these tracts code for a symptom, we came up with a technique called DBS fiber filtering. How does that work? We just, first of all, come up with a set of tracks. This could be a pathway atlas, but it could also be a connectome, right? It could be a normative connectome that I just threw under the bus, but any set of tracts that is available in a standard space, we can use for DBS fiber filtering. Now, what we do is we go track by track. We take one out, and we essentially look at how much is it modulated by each of our electrodes, right? We model the fields, we look at what's the impact of each electrode on the tract, and then there are three scenarios, like three classes of scenarios, each weighted a bit and statistically analyzed. But the first one, most easy one, is all the top responders modulated this tract, all the poor responders did not. So this is a good tract. Let's color it, orange, or color it red, or positive as a heat. And give it a strong, statistical value, usually an R value or a T value, right, depending on exactly the stats we apply. The opposite is also easy. All the poor responders modulated this tract, but the top responders did not. So this is maybe a detrimental tract that even hurts the symptom or makes the symptom worse. So we want to give it a negative weight and negative color. And then the scenario 3 is the jury is out, right? We have no clear relationship between who activated this tract and who got better. So this seems to be a irrelevant tract. So we filter it out. That's how fiber filtering came across. We now do this for every single tract in the connectome. We come up with a clear segregation of which tracts code for a symptom, and maybe positively or negatively, and the ones that are irrelevant get filtered out. This is an example for tremor tracts that associate with improvements of tremor, and that's the DRT we are seeing in red here. So fiber filtering is essentially isolating tracts that matter for any given symptom. And I want to show one example here where we applied it to Alzheimer's disease. People that have been here last year have maybe seen a few slides on this in the Talairach lecture by Andreas Lozano. And he's the one who started the whole story a while ago, 2008, in Toronto, so here in Canada. Him and others, Clement Hamani was also in the surgical room, operated on a single case with morbid obesity that was treated with deep brain stimulation. And when they switched on the electrode at 7 volts, all of a sudden the patient reported, oh, I see something. This is something, I see something from my past. This is a scene that's vaguely familiar. I know I've seen this before, but it's from my distant past, maybe from my childhood. Switched it off again, scene went away. They switched it on again and even increased the voltage. And then there was more details in the scene and more, even colors in the scene, even more volts, more details. Oh, it was night actually, and it was, these were the colors. So this was a flashback. And then Lozano thought, oh, we are close to the fornix here. This is part of the PAPE circuit. So maybe this could be a treatment for Alzheimer's disease and memory dysfunction. And that led to trials for actually putting in fornix-DBS into patients with Alzheimer's. So this is a typical example that happens so often in the literature of functional neurosurgery. It's serendipity, right? You find something, and it doesn't really come from animal models. There's no single example really that had a real breakthrough in functional neurosurgery that came from animal models, but it's usually these things we find in single cases that lead to actual discoveries in humans. Now, we came in much later than this. This is work by Ana Rios Infante, who was a master student in the lab, and we were fortunate to receive data from 46 patients from the phase 1 trial and the first advanced trial. And Anna put in a lot of work to use WarpDrive to register the patients. They had a lot of atrophy. It wasn't an easy task. And we then segregated the cohort into a training cohort of 28 cases and a test cohort of 18 cases. So we first look at the training cohort now. So what we find if we apply fiber filtering is that these tracts that we see here in red correlate with clinical improvement along the ADAS-Cog scale that's measured in this trial. And it is the fornix, right? It really is the PAPE circuit. It is also the stria terminalis. And in fact, the sweet spot is really in this crossing site between these two tracts here. Again, this maps beautifully to the PAPE circuit. And if we look at specific cases, we carried out leave one out cross-validation of this. Some would modulate the tract, some don't. And these really correlate with clinical improvement. So the more patients activated all these fiber tracts that were identified, the better the improvement, and the opposite. And then we could use the same network now from the training cohort to cross-estimate the unseen cases in the 18 cases in the test cohort. And again, we have two examples here, but again, the cross-validation really worked quite well. So the more patients hit this track, the better the improvement, and the worse, and the opposite as well. So we thought this is great. This was a robust effect, and but diffusion MRI can only take us so far. It's monosynaptic estimation. So how about the polysynaptic brain network that we can look at with resting state fMRI? So here we applied the same thing, but just using fMRI. Essentially, we found 3 times the same network, right? So this is the training cohort, this is the test cohort, this is the combined cohort. And if we put this into Neurosyn, we can look at all the other 1,307 networks that have been reported based on task fMRI and look at what's most similar. And the first things that came up were retrieval, memory retrieval, episodic, and then there's the outlier pain. I don't know why, but that's the outlier. Then task, then demands, then working memory. So the first 7 tasks that most resemble this network were all related, except with pain, to memory in general. And this is the summary. We could explain clinical improvements just looking at the local sweet spot level. Again, this intersection between stria terminalis and fornix. We could look at the tracts, and we could also look at the polysynaptic network. And as you can see here, we ran lots of cross-validations on all of these levels, and it was almost all significant. That's the one outlier where the p-value was not significant. But this seemed to be really robust, no matter how we splice up the data in the end. Now you might think, what about the flashbacks? We thought the same. Improvement in the ADAS-Cog is not a flashback. You don't want DBS to induce flashbacks all the time. So it has to do with memory, but it's 2 different things, right? So we looked at the flashback data, ran it into fiber filtering as well. So these are now different, simulation volumes, many more because they tested a lot in the operation room. And drum roll, out came a very different network, not the fornix at all. This is the anterior commissure. So what's the anterior commissure? Scratching heads, looking at brain anatomical books. Oh, this seems to connect the bilateral frontal poles. Frontal poles, flashbacks, rings a bell, but I don't know. Let's think. We're in Montreal, right? We're in Montreal. That MNI brain, MNI space. Oh, and who the neuro? Okay, so maybe we can discover together what could this be, right? Temporal lobes and flashbacks. Let's enter the MNI. Maybe, Camilla Golgi, Ramon Cajal. Maybe we find something. Oh, there's something. Wilder Penfield. That's the one. Yes, of course. I'm having a flashback about flashbacks now. So, of course, right? He stimulated the cortex, and he did stimulate everywhere in the cortex, but he also stimulated the temporal cortex. And we see that these are the sites that elicited flashbacks when electrically stimulating this temporal cortical. This is the same thing. And the AC connects this with, yes, if we draw this in and compare it to our network, it really seems to be this network, right? So this is such an interesting historical development. We had the flashbacks. They led to, could be fornix, led to trials. These trials were more or less effective, right? And the effect on the cognitive decline was the fornix. Lozano was right, but then the flashbacks themselves that led to the whole thing were likely more due to the anterior commissure. And we say, serendipity is concluded. Hello, Penfield. We are in Montreal. You might think, okay, this is all great, clinical improvements and clinical stories, but can we use this technology to also map the brain with human brain mapping? Can we study the brain with it, right? I brought one study along, which I think shows that we can. And it deals with the subthalamic nucleus, which is a small structure in the base of the thalamus, below the thalamus. Absolutely no worries if you haven't heard of it so far, but it is interesting because it receives input from the entire frontal cortex. So it's a bit like thalamus in small, right? Interestingly, it's also the most used DBS target worldwide for Parkinson's disease, and with that for any indication. But also interestingly, it's also used for dystonia, Tourette syndrome, and OCD. Wait a minute, the same small structure, a centimeter long, can be used to modulate all of these 4 diseases that are so different, like OCD and Parkinson's. Is that really true? You might now think, oh, maybe DBS is all sham, maybe this is all just placebo, right? If that doesn't make any sense, does it, right? I hope I convince you it does. So we set out to look at this in more detail, and this great work by Barbara Holunda, who's a PhD student in the lab. And, we brought together a lot of collaborators. So again, thank you for so many people that collaborated with us and shared their data. Localized electrodes from 4 different diseases, more or less the same thing we do for these 4 diseases. So we run sweet spot mapping, looking at which sites are optimal. We already see a gradient. The dystonia sweet spot is in the sensory domain of it. Tourette's in M1, and there's also a sidearm more anterior here. And then we have Parkinson's disease in SMA territory, and OCD maybe in DACC territory. Again, this is just a centimeter long, right? This is really, high resolution neuroimaging we're trying to do here. If we now use the Connectome again, or a tract atlas, and we just look at the connectivity from this, from these electrodes, they look more or less the same, right? But if we apply fiber filtering by filtering out the tracts that are not relevant for symptom improvements, we see a clear segregation. Can see it best if we show all tracts together. This is dystonia in the back coming from S1, M1, and then Tourette syndrome with these 2 arms, M1, also some frontal connection. We're quite certain by now the main Parkinsonian effect is really about SMA. And then OCD, we've replicated this tract quite a bit, and we'll zoom into that in a second as well. So this demonstrates in a way that we can maybe use DBS network mapping and fiber filtering to segregate the human connectome, and do so using somewhat causative inferences, or at least these electrodes really do something with the brain. So the fiber tracts are not causal, but the effect of applying DBS is some causal intervention we put to the brain. So it might be a nice way to look at the connectome with a flashlight from below, and looking at where do specific networks end up. If you're interested in this, Barbara Holunda will have a talk on Monday, 11 a.m. oral session, but also poster number 1354, Tuesdays and Wednesdays. Now let's zoom into OCD a bit as well. So this is the tract, the OCD tract, and that has a backstory that started before what I just showed you. OCD is very interesting from a DBS network mapping perspective, because there have been many targets that have been proposed in the literature, and the jury is still out which one is best. So that in a way screams for connectomics, because it might be one network that people target from different nodes. We were super fortunate to collaborate with the Cologne team, who had 22 cases operated with target of the anterior limb of the internal capsule, which is the ALIC. And also with the Grenoble team with 14 cases implanted in the SDN, our friend that we just talked about. Now, if you just look at the connectivity profiles seeding from these electrodes, they look different. No surprise, different brain areas have different connectivity profiles. But if you use fiber filtering, and red is good here, we see the same tract codes for OCD improvements, the same bundle here that you can see. And that's independent from one another. We can go one step further and essentially calculate the tract based on the ALIC cases, then put in the stimulation volumes of the SDN cases. And the more they hit the tract here, the better they became. So this is a cross estimate across DBS targets and DBS centers using a single tract model. Can do the same reverse. We can calculate the tract based on the SDN cases. The red tract matters here, and we see simulation volumes in the ALIC. And again, the same happened. The more this tract was modulated, the better the clinical improvement was in these cases. If we look further in the literature, other targets that have been used really seem to cluster along this tract, and some seem a bit, ventral, but these are electrodes sticking up like this. So really most of the targets really modulated this specific bundle. And then if you look at the distance between each site and the tract, that correlates with the reported average improvement in the Y-box scale as well. This is just 6 data points, but again, another small hint in the puzzle that this tract seems to matter. We showed this at a conference, and the London team was there, and then there was a rotational student in my lab. So we had 2 more data sets to validate this from. Again, we calculated the tract. By then we had a preprint. It was already out in the world, right? we calculated it based on the 2 cohorts, and then pressed correlate, and we're super excited, of course, that it was able to significantly estimate outcomes in these 2 additional cohorts as well. What's even better is if other people validate your work, right? We were, of course, super excited when the Mount Sinai team, led by Martin Figuet and Andrew Smith, came up with their own 10 cases. We had published the tract model openly inside of Lead-DBS. It's all in there. Everybody can test it and validate it or falsify it. So again, the more these 10 cases modulated the tract, the better the wirebox improvement was. And over the first 6 months after we published our report, we had, in fact, 4 validations by others that had used this and looked at this. So this is, to me, also the power of open science and open source. Everybody can use Lead-DBS. Everybody can use the tract. Many centers have data sets, so they can test it, right? They can, if that weren't the case, we would not be able to be so rapid in things. The last thing we did was a blinded replication. So 10 additional cases from Samir Sheth in Texas. He sent us the neuroimaging data and the simulation parameters. That's all we had from these cases. We ran it through the tract model, and we predicted the clinical improvements from these cases, sent them back to Baylor. That was a nervous email to send. We had to really put our nickel down. We had to, can't tweak anything. And, once the email is sent, that's what you really think. And then sure enough, Samir and his team knew the actual clinical outcomes, and both teams were super excited that the predictions really made sense. Now, recently we got a email from Eduardo Alio in Sao Paulo, who operated on a case inspired by this work and put in the electrode directly at the hub of this tract, and put it in, switched it on. It was a severe case of OCD, 32-year-old male with 14-year suffering history, severe symptoms, had undergone TMS, 2 different regimens of TMS and different things, of course, behavioral therapy. Nothing had really helped him. And then one day after this, they already received the call from the family and from the patient that there was a remarkable difference. And then 3 months, which is quick, very rapid, afterwards they came back in, did another Y-box, and it improved by 77%. So this is first anecdotal evidence, but it shows a prospective validation of this tract that we hope to build upon in the future. And in fact, the tract makes sense if you look at the history, right? There's cingulotomies that help for OCD. There's capsulotomies, that help. There's DBS in the ALIC here. There's DBS here. There's TMS up here. So it really seems to be this network of the ACC to the STN. And of course, there's a cortico-basal ganglia thalamocortical loop that is at play here. You might wonder now, okay, this is great for the average OCD case, right? But everybody's different, especially in OCD. So some patients will have a lot of obsessions, others have a lot of depression and anxiety. So we set out to segregate this tract with another big collaboration, also led by Barbara Holunder. Again, thank you for so many great colleagues that shared their data with individualized sub-item improvements. And this is, all that we localize, all these electrodes, all these, active contacts here. Again, Herculanean effort by Barbara. She's here as well. And we could, by doing so, essentially segregate the tract into sub-symptoms to obsessions, compulsions, anxiety, depression, and so on. And in the future, if this is further validated, we might be able to personalize. We put the electrode in, and then if the patient has a lot of anxiety, we stimulate a slightly different contact to modulate this tract versus another tract, and so on. So this is really exciting work that's coming up now. If you're as excited as I am on this, Barbara has a talk on Monday, 11 a.m. and also poster number 1353. That's Tuesdays and Wednesdays. So feel free to look at that as well. We can similarly zoom into Parkinson's disease. And this is work by Nanditha Rajamani, who is another really bright student and the second main developer of Lead-DBS after Ningfei Li. I'm no longer that important, but Ningfei and Nanditha currently really are the people that drive this toolbox effort. And she has looked at the same thing, looking at symptoms in Parkinson's disease. Here as well, you'll have some patients with a lot of tremor, others will have a lot of bradykinesia and axial symptoms. So zooming into the SDN, we could segregate this tract further. And interestingly, there are also different symptoms that seem to approach the SDN from different sides. What is also interesting is that for the axial symptoms, there is a connection to the brainstem, which is no surprise because it really goes towards the pedunculopontine nucleus, and people have actually put electrodes into that nucleus for gait problems. And then for tremor, there's the cerebellothalamic tract that comes along the SDN, and that's also part of it. Also no surprise and quite validated already. If you're interested in this further, please check out Nanditha Rajamani's poster number 410 or the oral presentation that she will give in the same session together with Barbara and Garance on Monday, 11 a.m. You might now think of non-motor symptoms, right? So what are the non-motor symptoms that are important in Parkinson's? So this could be depression, this could be apathy, this could be, cognitive decline and so on. There are usually batteries of numerous symptoms before and after surgery. And Garance Meyer, who's a postdoc in Boston side of the lab and also here at the conference, thought we could now burn all of these scores into a PCA model, essentially into fiber tracts. So each PC would code for one fiber tract. And then we can see which of these tracts are being modulated again and reverse the PCA to look at the predicted clinical outcomes on each of the scores. We came up with this not as clear model. It makes sense that it's anatomically not as clear because these PCs intertwine a lot and they are essentially mixtures of data compression. But if we look at how much of these tracts are being modulated, the combination of these, we can actually explain the variance in all of these improvement scores. So this is still work in progress, but in a way we could potentially condense things into different tracts and then use this model to explain a variety of clinical improvements. If you're interested in more of that, Garance is here as well. Also has a talk Monday, 11 a.m., same session as Barbara. Poster number is 1355, and that's Tuesdays and Wednesdays. So looking at this, we might come to a situation in both Parkinson's and OCD where we have these tract models. And the current situation is that we have the electrode implanted. We have one single VTA, volume of tissue activated, that tries to modulate all of these tracts together, right? That's maybe how we do it right now. And it works, right? It works really well. But maybe in the future, we will be much more deliberative. We already have electrodes with 16 contacts where we can stimulate to the side and so on. We could say, so this specific patient suffers from a lot of tremor and axial symptoms. We know tremor responds to high frequency, axial symptoms or gait especially rather to lower frequencies. So we could put different frequencies on different contacts of the electrode to personalize the treatment by doing so. In the remainder of the talk, I want to switch to resting state fMRI again. This looks at polysynaptic whole brain connections using the same thing. It all started in a first paper together with Michael Fox, where we used DBS electrode models, looked at where they map to the normative functional connectome, and we came up for each of them with a fingerprint. And we had two cohorts again, a training and test cohort from two different DBS centers back then. And looking at the fingerprints of each of these electrodes, we can see that they look quite similar. There was this normative functional connectivity, but looking at specific voxels, we see that some, for example, would be positively connected to M1 and some quite negatively, right? This was exactly the poor responding case of these 12. We analyzed many more of them, but these are just some examples. Now, based on that, we came up with this optimal connectivity map from the training cohort, and we could cross-estimate improvements in the unseen, test cohort from Würzburg. This was the first time we ever had a model explain, DBS effects across surgeons and DBS centers. And it was also the first time to use the Connectome to do so. Now, some of you that are a bit more familiar with DBS for Parkinson's would know that we have the subthalamic nucleus as the main target, but there's also the internal pallidum, and both work more or less the same way, right? So in fact, there are these randomized trials, and the jury's still out, and nobody has really come up with evidence to say this is the better target of this, right? So It's also a bit of a small fight between the US and Europe. I think in the US, the GPI is a bit more popular in some centers, and in Europe, maybe the STN could have historical effects, but there's no clear data, right? And we thought, okay, if this worked for STN DBS, we should get the same answer for GPI DBS. If not, there's no causality here, right? There's no, then it's just a spurious correlation. So Leon Sobieski in the lab looked at this and ran the same exact story based on a GPI cohort. And voila, the network really looks very much the same, right? We could even use the one derived from STN to estimate the patients from the GPI and vice versa, right? So in a way, we could cross-predict again across targets, now using functional connectivity. And this was also across surgeons, across DBS centers, across 2 different sites in the brain. And if we believe this story, right, coming from here or here, close by to one another, what we need to do is modulate this whole brain network, right? This network. How could we do that to modulate this network? We see it, right? It's right there. How can we modulate this? We can, of course, put these electrodes in there, but maybe we can do it from the outside. Maybe if only we could, right? If only we could put electrodes on here, put current on here. You see where I'm going, right? There are these multifocal, non-invasive forms of neuromodulation. This is TDCS now. We can fit the array, the electrode array, in such a way that it exactly matches the fMRI map I just showed you. And we did so, right? We ran a pre-registered clinical trial. We always, before we did so, we always talked about this. We always said, we should do this. We should do this. Mike Fox talked about this as well. Everybody in the field, yeah, we put these maps out. We should do this, but then nobody ever did. So we thought, okay, let's just do it. And I told Lucas, I don't believe this is going to work. I didn't believe in TDCS, if I'm honest. Sorry if I offend anybody here, but I really said, doesn't make so much sense. But let's try. We have to try. We did it the best way we could because we knew if it would fail and we did a mistake, then people would just say, you just didn't do it right? So we pre-registered it. We had blinded examiners and patients, blinded video ratings, and it was sham controlled, of course. And the software decided sham versus active stim. So we didn't even know while we were in the room. And I must be honest, Lucas was in the room, not so much me, but he did a great job doing this. And in fact, there was a significant effect on the UPDRS, on the Parkinsonian rating scale that is, was significantly different for stimulation versus sham. And it was a small effect. It was just 3 points on the UPDRS. For any clinician out here, they would agree this is not a big effect, but it was a clear effect, and it was 20 minutes only. So now I'm thinking, okay, maybe we should do this every day. Maybe we should do it every night, the whole night. Maybe we should stimulate longer and so on, right? So maybe we should follow up because there is a small effect, but a significant effect. And there's one more thing of this study where 6 of the patients, while we were writing it up, went on to get DBS. So we thought maybe there's a correlation of the effect that DBS had and TDCS had, right? And again, it's only 6 cases. I'm not even showing the correlation plot here, but there was a quite stark and large correlation, even significant correlation between the TDCS response and the DBS response. So potentially, I'm speculating here, but this could serve as a screening tool before we undergo DBS to first modulate from the outside and then see, is there an effect on that network? And in fact, the other thing is we have these fMRI networks for many diseases now. I'm just showing 3, but, we looked at this, across the field using Lead-DBS, not just us, but others do this all the time now. We have these maps now, right? We could essentially translate all of them to non-invasive stimulation. And in some diseases, it might be more interesting than in others because Parkinson's is neurodegenerative and goes down no matter what you do, but maybe depression is different. We could lift up people from their depression. So I want to conclude with what's next. That's always the most fun part. I can just talk about new cool things we're doing. So one challenge of the lab would be to connect the dots, right? We have these maps, as I just mentioned, for many diseases. We want to archive them better, to come up with a symptom network library and cross-link them. There's one example I can show already between depression and Parkinson's and depression in major depression. Shan Siddiqui and Mike Fox ran a beautiful study where they compared depression outcomes in DBS with patients with major depression and then non-major depression patients, including our Parkinsonian patients, but also patients with epilepsy. So they could show it's the same network, no matter which is the disease that codes for depression. And in fact, they could even show that you can derive the same network using brain lesions, TMS and DBS. There's also potentially a link to genetics. The Allen Institute put out this beautiful data set from 6 donors with transcriptomic profiles of a lot of genes, right? A lot of you have published on this. We also thought to give it a spin and link that to the connectome. You know, for each gene, we can, based on the gene expression profile in the functional connectome, we can come up with a functional gene connectome. We can link that onto systems as well. Like dystonia, all genes that code for dystonia, all genes linked with OCD. I know there's a weak link there. And then all genes that are associated with Parkinson's disease, come up with a network and use that to explain the outcomes in DBS for these diseases, right? And in fact, in these 3 examples, it really worked quite well. If you're interested more in this, you know, transcriptomics and translating the transcriptome to connect it with the connectome, speak to Clemens Neudorfer, who has a poster here at the conference, poster number 645 on Sunday and Monday. As a last point, I wanted to share that we are currently in the passage of transferring some of these concepts to the operation room. This is work by Simon Oxenford, who's a PhD student in a lab, who came up with a software called Lead-OR, where we can look at where the electrodes enter the brain in a histological atlas, but also in the patient data. And we can see what we record from these electrodes. These are 3 electrodes, 2 are inside the SDN, 1 missed it, right? We can see the one that's missed it down here quite easily. It's in white matter. There's not a lot of, you know, firing and spiking going on, but in the SDN, we see a lot of neuron activity. Now, the magic happens when we fuse this together, right? When we put the firing onto the anatomy of the brain. We can see this one again being outside of the SDN, but the other 2 just enter the SDN now. And we see a beautiful mapping and correspondence between the firing pattern and the reconstructions from Lead-DBS. As a next step in surgery, we test stimulate, right? We apply some voltage onto these electrodes already. And we can model that in real time as well with a spherical model that you know, we put in more voltage, the ball increases. And we can look at the fiber tracts activated. In red, we see the hyperdirict pathway, but in blue now, we see the internal capsule, which is responsible for capsular side effects that we can see in the operation room with the EMG, but also with, you know, examining the patient. You can see that this posterior electrode had, you know, capsular side effects much quicker already at a smaller volume. You see the blue tracts coming in. So we can choose this, you know, 3rd one here to be the best contact and use the software to visualize our thought process and then communicate that to the surgeon and make that decision together. So with that, I want to sum up. I hope I could convince you that Lead-DBS might be for not everybody, but some of you, right? It could be interesting to download it and look at some of the atlases or the tools we have in there. I hope I could show that we can use DBS network mapping to study the organization of the human brain and the connectome by, for example, segregating the frontal cortex with the SDN DBS network mappings. I showed some examples where we mapped symptoms across diseases and maybe also mapped improvements across DBS targets. And then lastly, I showed how we can use connectivity maps that came from invasive neuromodulation to stimulate non-invasively. And at the Center for Brain Circuit Therapeutics, led by Mike Fox here in Boston, where I currently work, we really aim for clinical translations in the center. We want to bring this into patients as fast and swiftly, but also, of course, as safely as possible. So we really work hard in trying to make some of this a clinical reality. I want to briefly mention a podcast that I run called Stimulating Brains, where I interview experts in the field. It's a lot of fun. I learn a lot myself by doing so. Got great help from Ala Taha, who's a student here in Canada and reached out to help. And 3 of my lab members started a talk series with the same concept where experts talk about brain stimulation. So if you're interested in this, it's all free and online, stimulatingbrains.org. please check it out. If you thought maybe this is a cool concept I want to apply myself, maybe this book is for you. We also have all the methods in there, all the basics, but then also all the applications. It really goes from A to Z. Lots of great collaborators that wrote chapters here. So please check that out. And then I want to thank my mentors, Michael Fox and Andrea Kuhn in Boston and Berlin. And I still currently have 2 labs across the Atlantic, an amazing team in Boston, an amazing team in Berlin. Thank you so much for listening to this talk. And I'm more than happy to take all the questions you may have. Since you're tuning in virtually, feel free to message me either on email or on Twitter and reach out with anything you might be interested in. So thanks again for your interest and for tuning in.